Rapid motion, G00, our first motion command. The G00 command is used to rapidly position the tool whenever it is not cutting. For example, when we need to bring the tool from the tool change position up to the workpiece, we want to do this as fast as possible. So we would command the G00 command. That would have the tool move as fast as it can possibly go. When we are all done cutting, we want to send the tool back to some tool change position. Again, we want the tool to get there as fast as possible. To do that, we use the G00 command again. Also, there are times when we're moving from one area of the workpiece to another area of the workpiece, when we are not cutting. In situations like this, we would also put the machine into rapid motion with the G00 command. Always remember, the G00 command makes the tool move as fast as it can possibly go. There is virtually no way to control how fast the tool will move when we command G00. Because the tool is moving as fast as it can possibly go, we should never wrap it directly onto the workpiece. You should always wrap it up near the workpiece and then feed onto the part. We'll demonstrate that a little bit later in this lesson. You must also understand that the rapid motion will not move in a straight line. Both axes will be moving at the same speed. So what we would think, going from the start point to the end point, that the tool would move in a perfectly straight line, this can't happen under the effect of G00, rapid motion. Let's take a look at the next slide and we'll see this graphically demonstrated. In this example, you can see as the tool is approaching the workpiece, it has a much greater distance to move along the z-axis. When the tool starts moving, at the beginning of the command G00, X and Z, the tool will start moving along both axes at the same time at exactly the same speed. Therefore, the tool will move at approximately a 45-degree angle down towards the left as it approaches the workpiece. But because the z-axis has a longer distance to travel, the z-axis will continue moving, whereas the x-axis stopped moving. You can see this same example played out in reverse at the end of the part. As the tool gets done machining the workpiece, it's going to go back to that tool change position. Watch as the tool moves up to the right at a 45-degree angle, and then it stops moving on x-axis and continues moving on z-axis. It is only important that you understand this so that you do not think that the tool will always be moving in a perfectly straight line under the effect of G00. When programming rapid motion, we need to tell the machine to go into rapid motion with the G00 command. We would then need to tell the machine where to position the tool using the X and Z words. X tells the tool where to position along the x-axis, and Z tells the machine where to position the tool along the z-axis. In this example, G00, X.5, Z.1 would position the tool at a half-inch diameter and 100 thousandths away from the face of the workpiece. This would be an approach position, as the tool would be coming from tool change up to the front of the workpiece. The Z.1, you will see that used quite frequently throughout this lesson, and that is just a safe approach position. Oftentimes you'll see experienced programmers positioning at a point of Z.05, or maybe even less in some cases. This is just a function of efficiency. We don't want to be feeding the tool any further than we need to. But for beginners, it is okay to use an approach position of Z.1. You should also note that we can move either the x-axis, the z-axis, or we can combine the motion with x and z axes. Doing this via program is very simple. To move only the x-axis, we would command G00 X and some position to move to. For the z-axis, we would command G00 and Z with some position to move to. When we are moving both axes at the same time, as we've been demonstrating with our approach movement and our return movement, G00 X some position and Z some position. If we command X and Z on the same line, we will be moving both axes. Otherwise, if we only command one or the other, only the axes specified will move. Let's take a moment and review what we've covered so far on rapid motion. G00 sets the machine into rapid motion. The machine will then move as fast as it can go, and you have no control over that speed. The machine will simply go as fast as it can possibly move. X and Z specify the position to move to. X would be which diameter, and Z would be what position along the Z-axis to move to. You can command movement on X, Z, or X and Z. The tool will not travel in a straight line when X and Z are commanded. Never, ever rapid directly onto the workpiece. Stop short of the part and then feed onto it. If you rapided directly up against the workpiece, granted the tool will stop without doing serious damage, but nonetheless you can almost be assured that you will be breaking the tool or damaging the tool in some way, possibly even doing something much more serious. Never rapid while the tool is cutting the workpiece. In other words, do not move the tool along the workpiece in the rapid mode. Sometimes a programmer or a setup person might try to get aggressive and reduce cycle time if they are cutting a soft material, for example plastic or perhaps even wax or aluminum. And they will think that, well gee, the machine just simply can't feed fast enough, so I'll put the machine into rapid motion and let it go as fast as it can. Granted, on some workpiece materials you may be able to actually cut at full rapid speed. However, you must never ever do this. It is very unsafe. You will not get the results that you expect, and it is going to cause all kinds of problems. So we would never ever rapid the tool while the tool is cutting the workpiece. We reserve the rapid motion for movements when the tool is not touching the workpiece. Just how fast will the machine go? Well, take a look at that chart below. In 1976, up until about 1985, the machines were rapiding at 300 to 400 inches per minute. Nowadays, in the year 1996 through 1997, the machines are going at 1,000 to 1,500 inches per minute. Now, just how do we get a perspective or a relationship to that? Well, let's put it into terms that we're all familiar with. At 25 miles an hour, driving in a car is a relatively comfortable speed, and most people would even consider that to be relatively slow. But take that to 1,000 miles per hour. It would be very exciting. Now, moving the tool at 1,000 inches per minute is also very exciting. Now let's see how that all fits inside of a program. In this program example, you'll see our tool call up command, our spindle start command, and then on the third line will be our rapid motion command. It's going to rapid the tool up to the front of the workpiece at a 1/2 inch diameter, and during that motion we're also going to turn on the coolant. Then we'll have a series of linear feed motions. Near the end of the program, you'll see us switch back to rapid motion with the G00 command. We'll move to an X position. Then we will rapid back to the tool change position, turning off of the coolant and finally stopping the spindle. Now this is a good example program for you to look at and see just when and where we would rapid the tool. Controlling the rate of feed with the F word. The CNC machine provides us with a way of controlling how fast the tool moves along while it is cutting the workpiece. This is called the feed rate. It is specified with the F command. This becomes active during the G01, G02, and G03 types of cut motions. It should be noted that there are two different types of feed rate on a CNC turning center. One would be inches per revolution, and the other mode would be inches per minute. The most common type of feed rate used on a CNC turning center is called inches per revolution. That is specified with the G99 command. G99 sets the machine into inches per revolution feed rate. G99 selects that mode, and the F word specifies the amount of feed rate. When in G99 mode, we are telling the machine inches per revolution feed rate. This means that as the workpiece rotates, the tool will move forward a given distance. In our example below, in one rotation of the part, the tool would move forward 7/1000ths of an inch. That would mean our feed rate is F.007, F 7/1000ths. That is inches per revolution feed rate. On a CNC turning center, this is truly the best way to program the feed rate, because if you remember, most of the time we would be programming the machine in constant surface speed mode, G96. That means that the RPM is going to be constantly changing, which really makes it extremely difficult to try and calculate a proper inch per minute feed rate, which we'll discuss next. So for right now, I want you to keep in mind that G99 is the most common mode of programming on a CNC turning center, and that our feed rate would be specified in inches per revolution, a distance for each rotation of the part. There are times when we need to use inch per minute feed rate, such as when we are bar feeding, or if you have special milling attachments on your CNC turning center. To select inch per minute feed rate, we would have to command G98. This sets the machine into inch per minute feed mode. With inch per minute feed mode, what we are really telling the machine to do is feed a given distance in 1 minute of time. Therefore, our feed rate becomes relative to time as opposed to the rotation of the spindle, as in the case with G99, inch per revolution feed rate. The problem with using inch per minute during cutting on a CNC turning center is, consider when we are in G96 mode. The RPM is constantly changing at any given moment. Therefore, the feed rate relative to the workpiece spinning would vary constantly. That is why G99 is so much used on a CNC turning center, because regardless of how fast the part is spinning and how much the RPM changes during the cutting condition remains consistent. It is always cutting at so many thousandths per revolution. Whereas if we were in inches per minute, that cutting condition would constantly change based on the RPM changing, as in the case of G96. Now let's take a look at the two of them together. With G99, we are telling the machine to feed in inches per revolution, so much distance for every rotation of the spindle. It would be used in almost all cutting operations on a turning center. And the spindle must be on in order for motion to actually occur. In fact, if the spindle is stopped, you will probably get an alarm on the machine telling you that the feed rate is 0. The general working range is approximately from the light end of cutting about 1/1000ths per revolution to a heavy end of about 20/1000ths per revolution. However, when we are into threading and so forth, you may see that the feed rate can easily get up to 100 thousandths per revolution, and even more. The G98 inch per minute mode is used mostly when bar feeding. The spindle can be stopped when you're feeding a tool. It is also used on some of the machines that have special milling attachments. The general working range for bar feeding is approximately from about 20 inches a minute up to 100 inches a minute. But that speed is really dictated by the type and style of bar feeder you have on the machine, as well as the size of the bar stock that you are feeding on the machine. In both cases, the F word would be used to specify the value for the feed rate. So for example, G99 and F.007 would be 7 thousandths per revolution feed rate. If we were under the effect of G98, as in G98 F20, we would be feeding at 20 inches per minute. But both commands would utilize the F word to specify the value for the feed rate. Determining the proper feed rate for any cutting operation requires you to look at some form of reference material. As you can see here, we are looking at a feed chart that is for turning, boring, and facing with coated carbide tools. If you look along the left-hand column, it's telling you what workpiece material you are cutting. In the second column, it says whether you're a rough operation or performing a finishing operation. The third column, DOC, which stands for depth of cut, is telling you what the ideal depth of cut is on the workpiece for good cutting conditions. The next column over, labeled SFM, is surface feet per minute. We covered that in an earlier lesson. And the last column is IPR, the inches per revolution feed rate for that tool in the specific work material. Keep in mind that just like with SFM, they are going to provide us with a working range, and we have to decide where in that range best suits our needs. Here we are looking at drilling cutting speeds and feeds. On this chart, it shows us the work material. In the next column, it is showing us the SFM for us to calculate the proper RPM for the drill. And keep in mind, on a turning center, we must program the RPM for a drill. We cannot program a drill to cut with constant surface speed. In the next column, and from there toward the end of the chart, it is giving us the IPR, inches per revolution, for that drill to cut in a specific material. But coming down a few columns, you will see that they are showing the drill sizes. You would select the feed rate based not only on the workpiece material that you are cutting, but also on the size of the drill. It only makes logical sense that a 1-inch drill can cut much heavier and much faster than a 1/16 inch drill. With turning, boring, and facing operations, the speed and feed chart will oftentimes give us cutting recommendations relative to the depth of cut, the DOC. It is important for you to understand that the DOC is the per side depth of cut. So as we are showing here, your depth of cut would reduce the diameter by twice the amount of depth of cut. So for example, if our depth of cut was 0.1 inches, the diameter would be reduced by 0.2 inches. Another way of looking at this, if our part was 2 inches in diameter, and we were taking 100 thousandths depth of cut, our cutting diameter would be 1.8 inches. Let's take a look at how we would apply this to a workpiece. In this example, we're going to be machining a piece of 303 stainless steel. We're going to be performing two operations. We will rough turn the OD and then finish turn the OD. So we must select the cutting conditions for this workpiece. as we look at the chart, we follow along the left-hand column and find 303 SS, short for stainless steel. The next column gives us our operation split, either roughing or finishing. So let's follow along with the roughing column first. The depth of cut should be between 0.1 and 0.5 of an inch. Now granted, 100 thousandths is a pretty good depth of cut for most machine tools. However, a 0.5 depth of cut should be reserved for only very, very large CNC turning centers. In fact, those machines would have probably in excess of 50 horsepower, very large. The SFM range would be 300 to 650 SFM, and our feed rate would be 6 thousandths to 30 thousandths feed rate. Again, 30 thousandths feed rate is probably very high for most machine tools. Coming across in the finishing column, we would see that our recommended depth of cut should be at a bare minimum of 20 thousandths and at the high end 100 thousandths. For the SFM, it is virtually identical to our rough cutting condition at 300 SFM to 650 SFM. And over to our feed rate for finishing, it would give us from 3 thousandths up to 15 thousandths per revolution feed rate for the finishing operation. Now that we have the general information, let's narrow it down a little bit more. For our roughing operation, I have decided that 125 thousandths depth of cut would be appropriate for my machine. 475 surface feet per minute falls right in the middle of the working range of 300 to 650 SFM. My feed rate that I have chosen is 0.009, 9 thousandths per revolution. Now you'll notice that that is not in the middle of that working range. In my example, I'm feeling that the workpiece might be a little bit on the less than rigid side, and that my machine could easily handle 9 thousandths per revolution feed rate. Going on to the finishing operation, I have selected 50 thousandths for my depth of cut. And I feel that a mistake that many beginning programmers will often make is that they go right for the minimal amount thinking that their tool life will be very, very long, when this is truly not the case. At bare minimum, your depth of cut for turning has to be greater than the radius on the insert. And considering that most finishing inserts have a radius of at least 15 thousandths and most typically 30 thousandths, we should have a depth of cut greater than 30 thousandths. So I pretty much standardize on a 50 thousandths depth of cut for finishing. My surface feet per minute fits into 475 SFM, which is right in the middle of the range, just like we selected for the roughing operation. And our feed rate is 6 thousandths per revolution. Now the feed rate for finishing operations is very different than for roughing. The feed rate for the finishing operation is going to control the surface finish, the smoothness of my workpiece. So I'm choosing a feed rate of 6 thousandths per revolution. And just as a general reference, by the way, an 80-degree diamond turning tool, as we have been showing here in these animations, with a 30 thousandths radius insert, at 6 thousandths per revolution feed rate will give us an approximately a 62 microfinish finish on the workpiece. When you are deciding on feed rates during roughing, as well as depth of cut and so forth, you have to take into account many factors, some of which are work holding, hardness of material, size of tooling, rigidity of tooling, horsepower of the machine, rigidity of the machine, condition of the machine, work material strength, and chip formation. Now what we have done was created a general chart here so that you can kind of look down the columns. If you have a lot of green factors, for example, your work holding is good and the the hardness of the material is soft, the size of your tooling is big, the machine is very rigid and it's new, you can kind of be aggressive on your feed rates, depth of cuts, and so forth. However, if most of your conditions are in the red zone, everything being weak, or the material being hard, or the machine being old and worn out, you might want to tend to favor the conservative side of feeds and speeds. But just for a little more general information, let's talk about the work holding. Ideal work holding is in a collet chuck or in a three-jaw chuck, wherein the workpiece cannot easily be pulled out or pushed out of the chuck. Castings tend to be a poor work holding condition. Hardness of material. You may think it's 303 stainless steel, however, 303 stainless steel can be in many different hardnesses, straight from the mill that created the material. So you kind of have to know how hard your workpiece material is. The size of tooling. If you have 1-inch square shank tooling, which is typical of most small to medium-sized turning centers, you can tend to push them pretty hard. But on some of the smaller machines where they have this miniature tooling of 3/8 or 1/2-inch shank tooling, you tend to have to be much more conservative with your cutting conditions. Rigidity of the tooling. Are the tool holders good and solid, or are they flimsy? The horsepower of the machine plays a tremendous role in selecting your depth of cut and the feed rate for roughing operations. Rigidity of the machine. Is the machine a good solid machine, or is it one of those lighter duty machines that tends to vibrate a lot when you're taking a heavy cut? The condition of the machine. Is the machine 10, 15 years old and pretty well worn out, or is it relatively new, say less than 3 or 4 years old, and it's a real good and tight machine, as well as in good condition? The work material strength. This kind of covers the size of the material. For example, you would not take a 1/4-inch depth of cut rough turning operation on a workpiece material that's only a 1/2 inch in diameter. You have to always take into account the size of your workpiece. If you're working with small diameter bar stock, you have to accommodate that with your roughing operations. You may have to go less than what is recommended just to fit within the capabilities of the actual workpiece. The chip formation. If this machine has any form of automation, automatic loaders and so forth, you may have to adjust your depth of cut and feed rates as well as the speed to accommodate good chip formation. Oftentimes on automated equipment, long stringy chips end up jamming up these loaders or bar feed operations. This is very undesirable. But as a programmer, it's kind of hard to predict what will happen as far as that goes. So that's really oftentimes left to the setup person. But anyhow, you should try to keep all of this information in mind as you're selecting speeds and feeds and any other type of cutting conditions. It is just not as simple as selecting the numbers out of a book. There's much more that goes into it, and many people believe that it's just plain and simply common sense. Here we have written the program for the roughing of this workpiece using the cutting conditions that we selected together. Please keep in mind that the size of the tool in the animation is not drawn to scale, so it does appear to be taking a very heavy cut. However, it does provide a good example of things that you have to watch for. Obviously, you can't take a depth of cut greater than the insert size of the tool. Now looking at the program, you can see that in the second line, G96 S475, that set up our 475 SFM. On the fourth line, G01 G99, G99 telling the machine to go into inch per revolution feed rate with a feed rate of F.009, 9 thousandths per revolution. Now if you look at the 3 roughing passes that we manually programmed into this part, you'll see that we're cutting at approximately 125 thousandths per side, or a 1/4 inch on the diameter. After we take our first 2 roughing passes, then we come back and take what is called a semi-finishing pass that smooths out the workpiece, and it leaves a consistent amount of stock on each diameter and across each of the faces on the workpiece. Look this program over carefully and watch the tool as it goes through the animations so that you see how the roughing operation is performed, as well as where the information goes into the program. The depth of cut during the roughing operation was programmed into the cutting passes. However, when it comes to the finishing operation, our depth of cut is controlled by how much our roughing tool leaves. In other words, when we are programming a roughing operation, we have to leave excess material on the workpiece so that our finishing tool has something to cut. So what we would be doing is leaving 5 thousandths on each of the faces in our last example, and 50 thousandths per side, which would total 100 thousandths on the diameter of the part. Again, it is important to understand that the depth of cut for finishing is controlled by the amount of material that is left on the part after the rough turning operation is complete. Now you can see where the feed rate and the speed gets put into the finish turning operation. On the second line of our program, you'll see G96, S475, MO3. Sets the machine into constant surface speed, 475 SFM, and turns the spindle on in forward rotation. On the fourth line of the program, you will see G01, Z-.375, F.006. That sets up our finishing feed rate. And again, our feed rate that we select for finish turning has more to do with what finish we want on the workpiece than anything else. Take a few minutes and look over this program real carefully. It serves as a good example of what a program should look like. You may want to backpage a few pages and compare it to the rough turning operation.